Hello everyone, this is topic 5, how structures fail. A little bit different sort of presentation method today, trying something new out. And so first of all, we're going to see if we can identify points of failure and modes of failure in natural and built structures. And so what we're looking at here is, first of all, levers create large forces. A lever is simply a device that can change the amount of force needed to move an object. This is something that you would have done in elementary when you discussed 3 different classes of levers. But when an effort force is applied, a very large force can be used to take a load. Now, in this case, here we see we've got the fulcrum right here. The lever is here, and with the use of a lever we could apply a certain amount of force here, but we wind up with much more force happening over here. Levers can create large forces which can cause unintentional damage to structures, and all the things that are underlined here, these are the things in which you're going to put in your notes. All the words that you need to be putting in your notes are underlined. Now, in the case of a flagpole in the wind, again, here you've got your fulcrum and the pole being a lever. What you can create here is where you put some effort here and you create a lot more force coming back this way. So you have a little force becoming a lot of force. Under compression, weaknesses can cause one section to shear. A building compresses soil can cause the ground to shear as the building tips. Again, you've got shear as being your word to fill in. And that winds up looking something like this. Here, we had all this area here wash away, which caused this whole building. This was being held up, this was not. We got the forces acting in opposite directions, and so we see that shearing force basically ripping this building down. Here again, something must have happened where causing the force to come down. Where this was supported, you've got the 2 different directions, and we call again that a shear force. Here's another example where we see that shearing happen. Now, under compression, thin panels can actually bend or buckle. Bend or buckle. Can look something like this, where there would have been a lot of force coming this way and causing this all to bend. Here again we see that bending under a compression force. In this case, the wall is actually bending in due to the weight of the house and being held up by the ground, and was causing all these cracks in along here as the wall is coming in. There is the additional force of the dirt pushing in, which is not helping the situation either. So if you were to draw this out, it would look something like this, where you start off with the one diagram and then everything kind of squishes and bends and buckles under compression. Now, torsion forces can cause brittle structures to also shear, and flexible structures to lose their shapes. Here we see where we've had one force come like this, one force come like this, which at the points here, we see it come and we see a shearing or twisting motion creating a shearing damage. Now, if it's flexible, it'll stay in place. The Tacoma Narrows Bridge is a great example of that, where we wound up with wind forces. The way the wind forces and the forces against it acting on the cables actually caused this bridge to wind up becoming very, very wavy under the wind. It's one of the engineering disasters of the 20th century. And here again we see that torsion force, this has caused it to completely shear apart. So this is your drawing. We see we've got the two motions. We've got that twisting motion, which causes that point of shear right here, which eventually will cause it to rip right apart. Now, making use of stress, the buckling or in the shearing can be used in many areas, which is actually being made useful. Metal fatigue can weaken metals when they're bent or twisted repeatedly, and looks something like this. I think this diagram should have been here. So making use of stress, if we think about this as making use of stress, these are shear pins on outboard motors. The idea is that it's a designed weak spot. And this pin is designed to break if weeds get caught up in the motor or something. And the designed weak spot means that it's going to break first, which will reduce the stress and means that the motor won't actually spin anymore. But it's also an easy place to get to and replace, rather than eventually causing extra damage. Cars also tend to have lots of crumple zones, areas that are designed to crumple up, and when they crumple up, that is going to put a lot less force and a lot less damage on the people who are actually in the car, because if you're in an auto wreck, it's more important for the car to be wrecked than the people inside. Some common ways in which we can prevent damage are with ribs and stringers. Pause the video at this moment and actually copy this out into your notes. Here we've got a rib, which is kind of just a piece in between. Here we've got a stringer moving alongside. Now we can combine the two. Here we've got the rib, and here we've got the stringers. All designed to help increase strength. Right, so we've got the making use of stress. Again, we've got the buckling. Car bumpers are designed to buckle in a collision, and outboard motors have shear pins. We've already taken a look at that. Now, spinning wheels can also be used to twist fabrics so that they tighten together and make a really strong thread, just with that kind of twisty motion. These sort of stresses are places where we've designed stress to actually be helpful. In the case of the car bumper, it's helpful in the fact that it's going to keep people safe. In the case of the outboard motor, it's saving costly repair. In the case of twisting, it's taking that flexible fiber and putting it back, twisting it, deforming it to a point where they lock together, and so you have a really strong thread. Okay, and that's your notes for lesson S5. If you have any questions, let me know.